Thank you for the host. And my name is Xiang, and I'm very happy to be here to show our recently work. And the topic of this work is an isotropic damage coupled cyclic plastic model for the whole life ratcheting of Carbide free Bainitic real steel. Most attention should be considered on the martensitic transformation. Okay, let's move. Firstly, I will introduce the research background and then the experimental observations. After that, more attention will be concentrated on the damage coupled model. After that, I will introduce the simulation results and some discussions. At the end, some conclusions will be presented. Okay, let's get started. First, the background of this research is on the heavy haul railway transport. Heavy haul railway transport has been globally acknowledged as a leading direction for the development of freight rail systems, owing to its high capacity, efficiency, and low cost. And the design axle loads of the heavy haul railways continue to rise. So the materials of the rail need to requires to offer significantly improvement of the wear and the fatigue resistance. However, the mechanics properties of the rail steels currently in service in China for short of meeting the increasingly demands demands operational conditions. We need to find another choice for the currently used pyrolytic heavy haul rails has reached the theoretical limitation of the fatigue resistance and the carbide-free Bainitic steel due to its low carbon content and structural toughness and ductility. So this materials is considered to a new generation of heavy haul rail steel. Actually, this materials has been used in some heavy haul lines, rail lines in China, like the Shitai lines, Yushan lines, and Shenzhen lines. Yes, we find the main failure modes is rolling contact fatigue, and we find the cracks on the catch corners. As the cycle loading increase, the spalling will be found. In addition, we also find the volume content of the martensite on the surface is lower than the other areas, and as the depth of the position, the volumes of the martensite is increased. So the rolling contact fatigue is related to the microstructure like the martensite or the returned austenite. In the practical wear and rail rolling contact, the rail experiences cyclic loading with the surface subject to combined rolling and sliding on the relative high contact stress. Extensive studies have identified cyclic strength and plastic deformation as the primary contributions to rail degradation. Whether contact induced stress exceeds the plastic shakedown limit of the ratcheting series hold, each cycle loading introduces incremental plastic deformation, which accumulates over times. So this phenomenon is known as ratcheting. Yeah. This finding highlights the critical role of the plastic ratcheting in rail rolling contact fatigue. To mitigate the risk of the catastrophic real failures on such demanding conditions, it's important to investigate the ratcheting behavior of the real steers. For the new materials, the ratcheting research is lack, and it's urgent to catch some related research. Okay, and most existing failure studies focus on the monotonic tension and the string-controlled fatigue of this material, and with a lack of fatigue experimental research on the ratcheting deformation and the patterns of the plastic deformation and the martensitic phase transformation during the ratcheting deformation and their effects on the fatigue damage still need to be clarified. So it's urgently need to conduct macro and micro scale experimental to studies the mechanism of ratcheting fatigue interaction in CFB real steels. For the model research and most existing constitutive models focus on the describing the effect of the martensitic phase transformation on the strength and the toughness, while models consider its impact on fatigue damage evolution are lacking. And the current research mainly address the influence of damage evolution on ratcheting formation, which limited attention on the effect of ratcheting fatigue damage evolution. So we need to develop a new model that considers both martensitic phase transformation and fatigue damage evolution. Let's see some observations of the experiments. The test materials is U20 minimum CFB real steels, and the microstructure of the CFB real steel primarily consists of lens like Bainitic ferrite and sheath like low Bainitic ferrite formed through a Bainitic transformation. And for the TEM observations in these figures reveals that both Bainitic ferrite and the martensitic lens exhibit a lens-like morphology, and the thin film-like returned austenite is in between the lenses. And for the macro experiment, we used the MTS machines to do some tensile and compression, and also some multi-axial loading paths. To investigate the evolution of the microstructure phase during the process, we conducted XRD experiments at a different number of cycles of the interrupter experiments, which can further to obtain some like the volume fraction of the return austenite and the dislocations density. And this is the fatigue results of the experiment. We can see with failures strength increase, the failures modes can be divided into the three types. Maybe the ratcheting dominant failure ones, and the fatigue dominant failure ones, and the combined one. So the ratcheting strain is maybe important to the fatigue life. And if we put all the strain controlled or strength controlled fatigue results into one figure, we can find that all the strength controlled life is less than the strain controlled ones. And as the mean strength and strength amplitude increase, the effect of the ratcheting strain is more obvious. Under the conditions with a large ratcheting strain, the failure modes is ratcheting failure modes, and in both the uniaxial and some multi-axial cases, ratcheting strings accelerates damage accumulation and reduce optical life. And we also find the microstructures evolution during the cyclic loading, and this one is string controlled and this one is stretch controlled. We find the dislocation densities under the string controlled model decreases rapidly in the initial cycles process reach constant values, but under the stress controlled, the circulation density is reduced slowly and do not reach a plateau. And for the volume fraction of the returned austenite, we also find the similar trends under the strain controlled. The volume fraction is decreases rapidly and reach constant value, and under the stress controlled, the volume fraction of the return austenite it decreases continuously and do not reach a constant value. Besides, we use the traditional way to evaluate the fatigue damage. We define the damage variable of the elastic modulus reduction, and also the shear modulus in another directions. We find that under the strain controlled models and under the stress control models, they still exhibit different trends. And with the existence of the ratchet strain, the damage increases linearly with increasing the cycle number. Also under the multi-axial loading path, we find still the differences between the string controlled and the stress controlled have different trend, and both in the axial damage and the torsional damage have the similar differences. So we conclude that under the stress controlled, that is the existence of the strings, ratcheting string, the microstructure evolution is different from the traditional string controlled one. Mostly is the ratchet string is accelerate the dislocations, substructures, and the martensite transformation is more easily happens under the stress control. Of course, this microstructure evolution mode is concluded with the evidence of others experimental observations, and I don't show in this presentation. And then we can see the damage coupled model. Firstly, the inelastic deformation and the thermodynamic framework should be introduced, and this framework is a classic elastic. Okay, is a basic elastoplastic framework, and for the given state, the Helmholtz free energy can be divided into the elastic one and unelastic one, and we can derived from the strength and strain, elastic and the damage relations, and most importantly, we introduce the phase transformation and the plastic interaction in this free energy. And the plastic strain rate and the transformation strain rate is used here. We have two inelastic mechanism and three dissipation mechanisms, and maybe should be quickly. And the plastic flow rulers is based on our previous work for the cyclically softening materials. And the phase transformation rulers, we introduce two terms to consider the transformation and the plastic interaction. And the damage evolutions, we introduce the Martin-Cytic transformation effect and the reaction string effect. And this is materials parameters used in this model, and the results show that our models have a good prediction results with experimental ones. Not only the string curves, but also the whole life, the evolution curves, and the fatigue life can be predicted well. And there's some the conclusions and some references and acknowledgements. Okay, thank you. That's all.